Chapter 2, Engine Systems, discusses the various diesel engine systems, their components, and how they operate. These systems include cooling, lubrication, air intake and exhaust, fuel, and the starting system. After completing this topic on the cooling system, you will be able to identify cooling system components and their function, the flow of coolant through a cooling system, and the characteristics of coolant. In this segment, you will learn the primary purpose of the cooling system and trace the flow of coolant through that system. You'll be able to locate and identify the function of each component in an engine's cooling system, and you'll be able to recognize different types of cooling systems. An engine's cooling system is responsible for maintaining adequate engine temperatures. If the cooling system fails, severe engine damage could occur. Let's look at the components and flow in a cooling system. The cooling system circulates coolant throughout the engine to remove the heat created by combustion and friction. It uses the principle of heat transfer to do its job. Heat always moves from a hot source to a cooler target. Source and target could be metal, fluid, or air. The key is the difference in relative temperatures between the two. The greater the difference, the more heat will transfer. Every component in a cooling system plays a role in heat transfer. The principal components in a cooling system are: number 1, a water pump; 2, an oil cooler; 3, passages through the engine block and cylinder head; 4, a temperature regulator and regulator housing; 5, a radiator; 6, pressure cap; and 7, connecting hoses and pipes. In addition, a fan, usually driven by belts, is located near the radiator to increase airflow and improve heat transfer. The water pump consists of an impeller with curved vanes in a housing. As the impeller turns, the curve of the vanes throws water outward and into the outlet formed by the housing. This is a typical water pump on an engine. As you can see, it's mounted to the front of the block. From the water pump outlet, coolant flows to the oil cooler. Oil coolers consist of a set of tubes in a housing. In this example, coolant flows through the tubes, removing heat from engine oil that surrounds the tubes. The oil cooler removes heat from the lubricating oil, which preserves the oil's lubricating properties. From the oil cooler, coolant flows either to the block, or if the engine is equipped with a turbocharger, it may flow to an aftercooler. Some turbocharged engines use a jacket water aftercooler. If so, coolant flows there next. The aftercooler removes heat from the intake air. On a jacket water aftercooler, the cooling system removes heat from the air. An aftercooler is constructed just like a radiator, with tubes and fins. The heated, compressed air coming from the turbocharger passes over the fins and transfers heat to the coolant in the tubes. From the oil or aftercooler, coolant flows into the engine block and around the cylinder liners, removing waste heat from the pistons, rings, and liners. These cavities are called the water jacket. Coolant travels from the engine block passages to the cylinder head, picking up heat from valve seats and guides. Once it leaves the head, coolant enters the thermostat or regulator housing. A temperature regulator is mounted inside the housing. The temperature regulator acts as the cooling system's traffic cop. The regulator's job is to maintain a proper range of operating temperatures. To do this, the regulator shunts coolant flow through the radiator or through a bypass tube back to the water pump. When the engine is cold, the regulator is closed. Coolant circulates back to the pump, bypassing the radiator. This helps warm up the engine. As the engine heats up, coolant temperature increases until it reaches the opening temperature for the regulator. As the regulator opens, some coolant is directed into the radiator. The remainder bypasses to the water pump. As temperatures increase, you should test the regulator. When the engine is cold, the regulator is closed. Coolant circulates back to the pump, bypassing the radiator. This helps warm up the engine. As the engine heats up, coolant temperature increases until it reaches the opening temperature for the regulator. As the regulator opens, some coolant is directed into the radiator. The remainder bypasses to the water pump. As temperatures increase, the regulator opens more and more coolant is directed through the radiator. When the regulator is fully open, all the coolant flow is directed into the radiator. You should test the regulator during cooling system maintenance and replace it if necessary. Opening temperatures are stamped on the regulator. If you should replace a regulator, make sure you use the one recommended for the engine, or else the cooling system will not operate properly. If the regulator is open, coolant flows through pipes or hoses to the top of the radiator. Up to this point, the coolant has been picking up heat from all parts of the engine. In the radiator, the situation is reversed. Coolant transfers its heat to the cooler atmosphere. In the radiator, coolant flows from top to bottom. Tubes and fins work together to dissipate heat. Radiators are usually mounted where they get the most airflow and best heat transfer. Radiators also have pressure caps. The cap determines how much pressure will be present in the cooling system during operation. Pressurized cooling systems help prevent water from boiling at higher altitudes. As you climb above sea level, boiling temperature drops. If the cooling system was not pressurized, the coolant could boil, causing serious engine damage. Radiator caps maintain pressure in the cooling system through two valves. If the difference between the cooling system pressure and atmospheric pressure exceeds the cap's opening pressure, an outlet valve opens. This allows a small amount of air to escape, reducing the pressure in the system. The system stabilizes. When you stop the engine and it begins to cool, the pressure inside the cooling system drops below that of atmosphere. The cap's inlet valve opens, allowing some air into the radiator. This evens out and stabilizes the two pressures. A variety of pressure caps can be used depending on the engine's operating altitude. The rated pressure is stamped on each cap. You should test the pressure cap during cooling system maintenance and replace it if necessary. Topic 3 will describe how to perform this procedure. Heat transfer across the radiator is aided by a fan. Fans increase the airflow past the radiator fins and tubes. Fans come in two types, suction and blower. Suction fans, such as number 1, pull air through the radiator. Blower fans push air across the radiator. Some engines use belts to drive the fan, water pump, or other components. If fan belt tension is too loose, fan speed can decrease. This decreases airflow across the radiator and reduces the overall cooling capacity of the system. Cooling systems are often modified to meet the special need of the engine application. Here you will learn about different types of cooling systems. A water-cooled exhaust manifold is sometimes added to a cooling system to cool exhaust gas before it's expelled. On marine engines, a water-cooled exhaust is used to keep engine rooms cooler. In a water-cooled exhaust manifold, coolant flows through a housing which surrounds the exhaust gas passages. Another option that may be present in some cooling systems is a coolant conditioner element. A coolant conditioner element can be connected in parallel to the coolant flow. Corrosion inhibitors are placed into it and dissolve into the cooling system during operation. On-highway trucks change engine speed frequently. Since the water pump is gear-driven, this means the flow of water through the system also changes speed. The cooling system has been modified to accommodate these conditions. Besides a water pump, oil cooler, coolant passages, temperature regulator, radiator and cap, fan and connecting hoses, truck systems have an additional shunt line linking the top of the radiator to the water pump. The shunt line protects the water pump from damage. As the truck changes speed, the gear-driven water pump changes speed. However, the coolant flow does not change speed as quickly, which causes a pressure differential at the water pump. The shunt line provides sufficient water to the inlet side of the water pump to maintain pressure and prevent the coolant from boiling. Water on the inlet side of the pump can boil because the pressure is reduced. On the outlet side of the pump, pressure is restored. This forces steam bubbles to implode. The bursting bubbles cause cavitation erosion at the water pump. Marine engines have several unique cooling system components because the heat from the engine is transferred to water rather than to air. Marine systems use a heat exchanger or keel cooling system. The basic coolant flow is the same, but a heat exchanger or keel cooler takes the place of the radiator. The components of a keel cooler system include the same components as a conventional system. There's a water pump, coolant passages, and a surge or expansion tank, which houses the temperature regulator. Instead of a radiator, the coolant flows through a keel cooler. The keel cooler is a series of coiled tubes. It can be built into the hull of the ship or mounted in channels and welded onto the hull. Coolant flows from the expansion tank, number 1, into the water pump, 2, through the engine and through the keel cooling coil, 3, where seawater cools the fluid. The heat exchanger cooling system includes a water pump, engine coolant passages, a water-cooled exhaust manifold, and an expansion or surge tank which houses the temperature regulator. There's also a heat exchanger. The raw water system has a raw water pump and pipes and hoses which transport seawater to the pump and to the heat exchanger. The heat exchanger is basically a hollow box filled with tubes. Engine coolant flows through the tubes. The tubes are surrounded by seawater. The seawater absorbs the heat from the coolant. Zinc rods are used in marine applications to reduce corrosion. Zinc is much more susceptible to corrosion than other metals found in the cooling system. When the zinc is exposed to seawater, the zinc corrodes instead of the other metal. This process is called galvanic corrosion. Zinc rods are called sacrificial anodes because they're designed to corrode instead of the other components. The rods must be checked frequently and replaced as needed. In this segment, you'll learn about the 3 ingredients of coolant and recognize the purpose of each ingredient. You'll be able to identify recommended antifreeze and coolant conditioner concentrations. And you'll learn about the 3 factors which determine the operating range of a coolant. Coolant is a mixture of water, antifreeze, and coolant conditioner. Each element serves a different purpose, and together they protect the engine from overheating, freezing, and corrosion. Water is the main ingredient for all coolant because water transfers heat better than any other substance. Water has several drawbacks as a coolant. It boils easily. It freezes. and it's extremely corrosive to metal. Antifreeze, or ethylene glycol, and coolant conditioner are added to correct these deficiencies. Antifreeze, or ethylene glycol, is used to raise the boiling point and lower the freezing point of water. The amount of ethylene glycol affects the boiling point. The more antifreeze, the higher the boiling point. If coolant freezes, it cannot flow, therefore it cannot cool the engine. Frozen coolant can also expand and crack castings. Freeze protection varies depending on the concentration of antifreeze. Conditioner prevents corrosion by coating all the components in the cooling system. The thin coating prevents water and cavitation erosion from attacking the metal. There are several variables which can affect the operating range of coolant. Operating altitude and system pressure affect the boiling point of water. Increasing altitude lowers the boiling point of water. Increasing system pressure increases the boiling point of water. This is why most cooling systems operate under pressure. Pressurizing the system raises the boiling point. Since most engines operate above sea level, they need this protection. Three factors influence the operating temperature range of coolant. First, the operating altitude. Second, the system pressure. And third, the concentration of the antifreeze. It is critical to prevent the coolant from boiling. If coolant boils, steam bubbles form. These pockets of air do not transfer heat well, which leads to overheating. Steam bubbles can also interfere with the water pump's ability to make coolant flow. This can lead to serious engine damage. When the steam bubbles break, they can remove small particles of metal from components. This is called cavitation erosion. To provide adequate protection to the engine, the concentrations of antifreeze and coolant conditioner must be in the correct proportion. To prevent cooling system problems, you should maintain a proper antifreeze concentration. When you mix coolant, it's recommended you keep the antifreeze concentration between 30 and 60%. Concentrations lower than 30% do not provide adequate protection, while concentrations above 60% start to reduce the heat removal properties. Antifreeze concentrations higher than 60% also reduce the freeze protection and contribute to silica dropout, which destroys seals and clogs the cooling system. Coolant conditioner is a good thing, but a little goes a long way. It's recommended you keep the coolant conditioner concentration between 3 and 6%. If the coolant conditioner concentration is lower than recommended, engine components like cylinder liners can corrode or experience cavitation erosion. Too much conditioner can cause silica dropout. Silica dropout turns the coolant into a thick gel, which damages the water pump and clogs the radiator. High concentrations of coolant conditioner also reduce heat transfer. There are several ways to add conditioner to the cooling system. Use only one method at a time to prevent over-conditioning, and check the concentration before making any further additions. Make sure you add the proper amount of coolant to the system. If the coolant level is low, there will not be enough water, antifreeze, and conditioner to protect the engine. Check the operation and maintenance manual for the correct fill level for the engine you are working on. In general, the coolant level should always come up to the bottom of the filler pipe. After completing this topic, you will understand the purpose of a lubrication system and be able to identify system components and their function. You will understand the key properties of engine oil and the flow of oil through the lubrication system. In this segment, You will learn about lubrication system components and their function. You will also be able to trace the flow of oil through the engine. The primary purpose of the lubrication system is to circulate oil throughout the engine. The oil cleans, cools, and protects the engine's moving parts from wear. The lubrication system consists of 1. An oil pan or sump, 2. A suction bell, 3. An oil pump, 4. A pressure relief valve, 5. An oil filter with a bypass valve, 6. An engine oil cooler with a bypass valve, 7. The main oil gallery, 8. Piston cooling jets, 9. A crankcase breather, connecting lines and pipes, and the oil itself. The oil pan or sump acts as a reservoir for the engine oil. The oil pan also dissipates heat from the oil to the atmosphere. The oil pan is located on the bottom of the engine block. From the oil pan, oil passes through an inlet screen and into the suction bell. The inlet screen prevents large pieces of debris from entering the oil system. The suction bell transports oil to the oil pump. The oil pump creates flow, which circulates oil throughout the engine. The oil pump is located in or near the oil pan. The pump is driven by the crankshaft via an oil pump gear. A pressure relief valve is normally located near the oil pump. The relief valve protects the lubrication system from high pressures. From the oil pump, oil travels through the oil cooler. Oil coolers remove heat from the oil. Oil fills the oil cooler housing. Inside the housing are tubes which carry engine coolant. Heat transfers from the oil to the coolant. The oil cooler also has a bypass valve. Oil flows from the oil cooler to the oil filter. Lubricating systems can use one or more oil filters depending on the design. Filters remove debris and metal particles from the oil. Filters use bypass valves as well. In a full-flow filter system, 100% of the oil goes through the filter. These systems must have a bypass valve. A bypass filter system uses 2 oil filters. 90% of the oil flows through the primary filter, shown here as number 1, and 10% flows through the bypass filter, number 2. Usually the bypass filter is more tightly woven to trap extremely small particles. Bypass filtering systems also use bypass valves. On some turbocharged engines, oil flows from the filter to the turbocharger through an inlet line. An outlet line returns oil to the oil pan. On other engines, clean oil leaves the oil filter and enters the main oil gallery. The main oil gallery is located in the block. This is the primary oil passage through the block. From the oil gallery, the oil flows to all moving parts of the engine, including the main bearings and crankshaft. Oil flows from the gallery to the crankshaft, which then lubricates the main and connecting rod bearings. Caterpillar crankshafts have drilled oil passages which deliver oil to the connecting rod and main bearings. Oil reaches the cylinder walls as it is slung out of the rod bearings and splashed off the piston undercrowns. Oil travels through passages to lubricate all moving parts, including the valve train, injection pump housing, timing advance unit, and other accessory components. Oil drains back to the oil pan through passages. The oil lines, passages, and bearings restrict the flow of oil, which creates oil pressure. Most of the oil system pressure is created by the main bearings. The oil pressure reading on a gauge is the result of this normal restriction. Piston cooling jets spray oil to the underside of each piston and will help lubricate the cylinder walls. Crankcase breathers vent combustion gases that leak past piston rings. This maintains stable pressures within the crankcase. Breathers are often mounted on top of the engine. This equalizes pressure inside the engine crankcase with pressure on the outside and permits oil to easily drain back to the oil pan. In the lubrication system, the oil filter requires the most maintenance. It does get dirty, and if not properly maintained, can cause lubrication system problems. Lubrication systems use several bypass and relief valves to protect the engine. Oil pumps use pressure relief valves, while oil coolers and oil filters use bypass valves. The name of the valve describes how the valve operates. Pressure relief valves reduce system pressure, and bypass valves allow oil to flow around a component instead of through it. The pressure relief valve is usually located near the oil pump. The relief valve is commonly a spring-actuated valve. The relief valve opens when system pressures exceed the spring force on the valve. As long as pressure remains high, the valve remains open. When the relief valve opens, some oil drains back to the oil pan. When oil pressure drops below the spring opening force of the valve closes. The oil cooler bypass valve is a directional valve that opens when the pressure differential across the oil cooler is higher than the opening force required to open the valve. When the valve opens, oil diverts around the oil cooler. This ensures that some oil reaches vital engine parts, even if there is an oil cooler problem. When the oil is cold, it may not flow well. This would open the valve. The oil cooler bypass valve is often built into the oil cooler. The oil filter bypass valve is a directional valve that opens when the pressure differential across the oil filter exceeds the valve spring opening force. If the oil is thick, such as at engine startup, or if the filter is clogged, the filter bypass valve opens. Oil diverts around the filter, which ensures that some oil always reaches the bearings and other engine components. This protects the engine from oil starvation damage. This segment, you will learn about viscosity, viscosity index, and TBN. Engines require the right type, the right viscosity, and the correct quantity of oil in order to operate properly. Oil must lubricate, clean, and cool engine components under a variety of operating conditions. Oil must flow and lubricate in cold climates and be able to withstand heat without thinning or breaking down. The Society of Automotive Engineers, SAE, has developed a classification system to describe an oil's ability to withstand extreme conditions without breaking down. Oil is described according to its type and viscosity. Oil type describes performance characteristics such as detergency, dispersancy, and resistance to breakdown. Oil type is identified with alphabetical letters like CE or CF4. Different engine models require different types of oil. Make sure you use the type of oil recommended for the engine. Refer to the most recent literature for the correct recommendations. Viscosity describes a base oil's resistance to flow. Flow relates directly to how well the oil coats and protects parts. Viscosity changes with temperature. The higher the temperature, the lower the viscosity, and the thinner the oil. Viscosity index, or VI, is a measure of the base oil's ability to resist viscosity changes with temperature changes. High VI oil changes viscosity less as temperatures change. Low VI oil changes viscosity more as temperatures change. It is important that the oil not become too thin at high temperatures. Thin oils do not provide enough protection against wear. Multi-viscosity oils have been chemically altered to extend their operating range. A lower viscosity base stock is blended with an additive, which thickens the oil as temperature increases. As multi-viscosity oils deteriorate, viscosity reverts back to the lower viscosity of the base oil. The oil label tells you much about the type and viscosity of the oil. The Society of Automotive Engineers classifies oil according to the letters SAE followed by a number. The number describes the viscosity grade. Single-weight oils have only one number. Multi-viscosity oils have two numbers. Lower numbers mean the oil is thinner. The higher numbers mean the oil is thicker. For multi-viscosity oils, the first number is the cold viscosity grade, while the second number is the hot weather viscosity grade. Winter and summer oils. Viscosity grade numbers with a W are considered winter oils, tested to have correct viscosity at 8 degrees Fahrenheit. Numbers without the W are considered hot weather oils, tested to have correct viscosity at 210 degrees Fahrenheit. Base oils are usually produced by refining crude oils. Base oil cannot provide enough protection and lubrication for today's high-performance engines. Certain oil additives have been created to improve and strengthen the oil. Common oil additives include detergents, which help keep the engine clean, anti-wear agents to reduce friction, dispersants, which keep contaminant particles in suspension, alkalinity agents to neutralize acids in the oil, oxidation inhibitors for preventing the oil from oxidizing when it's exposed to air. Oxidation causes development of organic acids and carbonaceous matter. There are also pour-point depressants to keep the oil fluid at low temperatures. Petroleum-based oils contain wax, which crystallizes at low temperatures. The depressants keep wax crystals from forming, and there are viscosity improvers, which keep the oil from becoming too thin at high temperatures. The most common oil additive you'll work with is total base number, or TBN. TBN is produced by adding alkalinity agents to the base stock. The more alkaline the oil, the higher the TBN, and the more acid it can neutralize. The amount of alkalinity additive in an oil is indicated by the total base number, or TBN. Diesel fuels may contain sulfur. When these fuels burn, the sulfur helps create acids. These highly corrosive acids contaminate the oil. The alkalinity additives within the oil neutralize these acids. This prevents the sulfuric acid from corroding metal parts. The TBN number of the oil indicates how well it neutralizes acids. Since different fuels contain different amounts of sulfur, it's important to use an oil with a high enough TBN. Follow the recommendations of the engine manufacturer. The alkalinity additives within the oil neutralize these acids. This prevents the sulfuric acid from corroding metal parts. The TBN number of the oil indicates how well it neutralizes acids. Since different fuels contain different amounts of sulfur, it's important to use an oil with a high enough TBN. Follow the recommendation of the engine manufacturer. Over time, the oil additives degrade, and the oil's ability to lubricate decreases. If you do not change the oil frequently enough, the oil will oxidize, additives will deplete, and sludge may form. After completing this topic, you'll be able to identify the major components in an air intake and exhaust system and describe how they operate. In this segment, you will be able to identify the components in the air intake exhaust system and identify the purpose of each. You'll be able to identify different air intake systems, including naturally aspirated, turbocharged, turbocharged aftercooled, air-to-air aftercooled, jacket water aftercooled, and separate circuit aftercooled. Diesel engines require large quantities of air to burn the fuel. The air intake system must provide enough clean air for combustion. The exhaust system must remove heat and combustion gases. Any reduction in the flow of air or combustion gases through the system reduces engine performance. A common intake and exhaust system includes, number 1, a pre-cleaner, number 2, an air filter, 3, a turbocharger, 4, an intake manifold, 5, an aftercooler, 6, an exhaust manifold, 7, exhaust stack, and 8, the muffler and connecting pipes. In order to service and troubleshoot the air system on an engine, it's important to understand the flow of air through the system and the function of each component. It's also important to know what the components look like and how they work. Pre-cleaners are often used in the air systems of diesel engines. The pre-cleaner screens out heavier, larger contaminants suspended in the air. Clean air is critical for peak engine performance. Dirt can increase wear and damage engine components. Air leaves the pre-cleaner and enters the air filter. The air filter prevents smaller dirt and debris from entering the engine. Clean air is critical for peak engine performance. Dirty air can increase wear and damage engine components. The air filter housing holds the filter element. From the air filter, the air flows into the turbocharger. Turbochargers help maintain engine power at high altitude. They also increase horsepower. Turbochargers provide the engine with more air, enabling it to burn more fuel. A turbocharger has two parts. 1, the air inlet side, or compressor, and 2, the exhaust side, or turbine. Exhaust gases from the exhaust manifold turn the exhaust turbine of the turbocharger. Exhaust gases spin the turbine side. Since the compressor and turbine wheels are on the same shaft, the compressor turns as well. The faster the compressor side turns, the more air is packed into the air system, increasing air pressure and density. The increase in air pressure is called boost. Wastegates are part of some turbochargers. If boost is higher than recommended, the wastegate opens to vent exhaust around the turbine. The reduced exhaust gas flow slows down the turbine and compressor, controlling boost pressure. The turbocharger provides more air to improve combustion. As the air compresses, it heats up and expands, becoming less dense. This means there may not be enough air for good combustion at higher fuel settings. Most turbocharged engines use an aftercooler to reduce the temperature of the intake air. Turbochargers increase the temperature of intake air to roughly 300 degrees Fahrenheit. The hot intake air is less dense. The aftercooler removes heat from the inlet air. As the air cools, it becomes more dense. This means that more air can be packed into each cylinder. Aftercoolers get their names because they cool the air after it passes through a turbocharger. Some aftercoolers are located between the turbocharger and inlet manifold. Others are found inside the intake manifold. From the aftercooler, air flows into the intake manifold and to the intake valve ports for each cylinder. The intake manifold is mounted on the cylinder head. Air enters the combustion chamber where it burns. Combustion gases exit the exhaust ports and enter the exhaust manifold. The exhaust manifold is mounted on the cylinder head and fits over the exhaust ports. From the turbocharger, exhaust gases are piped through the muffler and exhaust stack. The muffler deadens exhaust noise and makes the machine quieter. After exhaust gases pass through the muffler, they enter the exhaust stack. The stack vents the exhaust away from the operator. Exhaust gases enter the atmosphere from the stack. In addition to the basic components you've just learned about, marine and industrial engines may use 1. A water-cooled exhaust manifold, and 2. A water-cooled turbocharger. There are several types of air intake systems: naturally aspirated, turbocharged, and turbocharged aftercooled. Air intake systems that have neither a turbocharger nor an aftercooler are known as naturally aspirated systems. Some air intake exhaust systems have turbochargers but no aftercoolers. These are known as turbocharged systems. One of the most common air intake systems is known as a turbocharged aftercooled system. These systems have a turbocharger and an aftercooler. Different types of aftercoolers can be used. There are several types of aftercooled systems: jacket water aftercooled, air-to-air aftercooled, and separate circuit aftercooled. A jacket water aftercooled system uses engine coolant to cool the inlet air. The aftercooler housing fits inside the intake manifold. Engine coolant circulates and removes heat from the intake air before it reaches the intake manifold. Jacket water aftercooled systems are used on many mobile applications. Some air intake systems use outside air to cool the inlet air. This system is called air-to-air aftercooled. The aftercooler looks like a small radiator mounted in front of the coolant radiator. Ambient air blows over the aftercooler, cooling the warm inlet air. This is what a typical air-to-air aftercooled system looks like on an engine. Separate circuit aftercooled systems are most commonly found on marine applications. Water cools the inlet air, but the separate circuit aftercooled system and engine cooling systems are separate. A separate circuit aftercooled system has its own heat exchanger, pump, and water supply. After completing this topic, you will be able to identify fuel system components and their operation. In this segment, you will learn the purpose of the fuel system and how it operates. You will learn to identify the components used in a pump and line system and an electronic unit injection system, and identify the function of each component. You'll also be able to trace the flow of fuel through the system. The amount of fuel the engine burns is directly related to the amount of required horsepower and torque. In general, the more fuel the engine receives, the more torque is available at the flywheel. The fuel system delivers clean fuel at the right time and in the right quantity to meet engine horsepower demand. The fuel system components match fuel delivery to engine horsepower demand by altering how much fuel is injected and when it is injected. These functions are handled by the heart of the fuel system, the fuel injection pump. A pump and lines fuel system consists of 1. A fuel tank, 2. The fuel filters, 3. A transfer pump, 4. Injection pump, 5. A governor, 6. Timing advance mechanism, 7. A fuel ratio control, 8. High pressure fuel lines, 9. Low pressure fuel lines, 10. Nozzles, and 11. A return line. The fuel tank stores fuel. Fuel tanks are available in different sizes. You can find fuel tanks located in a variety of places, depending on the application. Fuel begins to flow when you turn the key to start the engine. As you turn the key, a solenoid is actuated, which allows fuel to flow from the transfer pump to the injection pump. The fuel transfer pump pulls fuel from the tank through the primary fuel filter. The primary fuel filter removes large debris from the fuel. Some fuel systems also have a water separator. The water separator allows any condensation or trapped water to settle out. Water in the fuel can cause serious engine damage. From the primary filter, fuel enters the transfer pump. The transfer pump provides flow throughout the low-pressure portion of the fuel system. The primary purpose of the fuel transfer pump is to keep an adequate supply of clean fuel in the injection pump. Fuel exits the fuel transfer pump and enters the secondary or final fuel filter. This filter screens minute particles and contaminants from the fuel, which could damage nozzles or plug injectors. Final filters are located between the transfer pump and the injection pump housing. Unlike oil filters, the fuel filters have no bypass valve. If the filters get clogged, fuel flow stops and the engine will not run. This protects the engine from dirty fuel. Most final fuel filters incorporate a fuel priming pump in the base. You can use the pump to prime the system if you've removed the fuel pump housing for a major service. The pump is also used to prime the fuel system after changing the fuel filter. Fuel exits the final filter and flows into the fuel gallery within the injection pump housing. Pumps in the housing measure and pressurize the fuel. The housing is generally located near the front of the engine because the pump is gear-driven from the camshaft. A timing advance unit, mechanical governor, and fuel ratio control are attached to the housing. On pump and line systems, steel high-pressure fuel lines connect fuel injection pumps to nozzles. The high-pressure side of the fuel system consists of the high-pressure lines and the nozzles. Proper quantities of pressurized fuel travel through the high-pressure fuel lines to the fuel nozzles. Fuel travels through high-pressure fuel lines to the nozzles. Nozzles are located in the cylinder head. Nozzles have valves that open when fuel pressure gets high enough. When the valve opens, fuel is atomized and sprayed into the combustion chamber. At the end of injection, there's a rapid pressure drop, which closes the valve. More fuel is available in the fuel injection pump housing than the engine can use. The return line directs excess fuel back to the tank, removes air from the fuel, and cools the fuel by keeping it in motion. The fuel system will not operate correctly without a fuel return line. Every fuel system has either electronic or manual methods of turning off the fuel supply. Electronic unit injection systems use some of the same components as a pump and line system. Electronic unit injection systems use 1. A fuel tank, 2. A primary fuel filter. 3. A fuel transfer pump. 4. A final fuel filter. And 5. A return line. The fuel injection pump is the point where electronic unit injection systems differ from pump and line systems. Fuel exits the final fuel filter and enters a fuel manifold. The fuel manifold is usually part of the engine block. The manifold is filled with fuel. The fuel injection pump, high-pressure lines and nozzles are replaced by a single component called a unit injector. Electronic unit injectors are mounted in the cylinder head. Fuel in the manifold enters the injector, which meters, pressurizes, and injects the fuel. Electronic unit injectors can be recognized by the solenoid attached near the top. On an electronic unit injection system, the mechanical governor, timing advance, and fuel ratio control are replaced by electronics. The system uses an electronic control module, or ECM, to house some of the electronics and programming information. The combustion chamber design affects fuel efficiency and engine performance. The design of the piston and the method used to inject fuel into the cylinder determine how quickly and completely the fuel burns. In pump and line systems, there are two types of combustion chamber design. 1. Pre-combustion chamber, or PC, and 2. Direct injection, or DI. In electronic unit injection fuel systems, there's only one basic type of combustion chamber, the DI. In a direct injection combustion chamber design, fuel is injected directly into the cylinder through the nozzle. In a PC system, the nozzle injects fuel into a pre-combustion chamber, where it ignites. This forces the remaining fuel into the main chamber, where full combustion takes place. In some engines, glow plugs are used to warm the air when starting the engine. To prevent burning a hole in the top of the piston, PC pistons have a steel heat plug mounted near the center. In this segment, you'll learn how a fuel injection pump, governor, and timing advance unit operate. You'll learn the advantages of a unit injection system, and you'll understand the meaning of low idle speed, high idle speed, overspeed, full load speed, and lug. Over the years, CAT has made significant design changes in the fuel system. The new designs have improved engine performance and reduced emissions. This segment explains two basic methods of fuel injection: mechanical systems, shown on the left, which use a governor, timing advance unit, and fuel ratio control, and on the right, electronic unit injection systems. In diesel engines, fuel is injected during the compression stroke, before the piston reaches top dead center. The basic principle of fuel injection is that the right amount of fuel must be injected at the right time to satisfy engine horsepower demands. Fuel requires time to burn. The right amount of fuel must be injected at the appropriate point in the compression stroke so that it burns completely. This is known as the burn window, shown here as number 1. The burn window is measured in degrees of crankshaft rotation. Degrees of rotation means the number of degrees the crankshaft rotates while fuel is being injected. The burn window is described by the starting point of injection, or timing, and the length of time injection occurs, or duration. Both timing, number 2, and duration, number 3, are measured in degrees of crankshaft rotation. In a mechanical fuel system, the fuel injection pump, shown here as number 1, combined with number 2, the timing advance, 3, the governor, and 4, fuel ratio control, all work together to control fuel injection. These components have a direct effect on engine performance. As engine load and engine speed change, varying amounts of fuel must be injected at different times in order to maintain the proper burn windows. A timing advance unit controls when fuel is injected, and the governor controls how much fuel is delivered to the engine, or duration. The fuel injection pump is the heart of the fuel system. Understanding how the pump operates is a critical first step in understanding fuel injection. In pump and line systems, fuel injection pumps usually have 1, a plunger, inside number 2, a barrel. The plunger moves up and down following the motion of the fuel pump camshaft. Low-pressure fuel in the gallery, 3, flows to and from the barrel through ports, shown here as number 4. The plunger has a groove or scroll machined into it, number 5. When this scroll aligns with the ports, fuel can flow from the inlet port through 6, the pumping chamber, to the outlet port. When the scroll blocks the ports, the fuel in the pumping chamber is trapped and forced to the nozzle. It is at this point that injection begins. This point is called injection timing and is controlled by changing the position of the fuel pump camshaft. It is the beginning of the burn window. Injection occurs during the time the ports are closed off by the scroll. This length of time is called duration, shown here as number 1. The longer the duration, the more fuel is injected. Duration is controlled by rotating the plunger in its bore. This changes the amount of scroll that exists between the ports. The ports are either shut off sooner, fuel off, or left open longer, fuel on. Injection duration is controlled by the governor and rack. All the fuel pumps are linked to the governor by the fuel control rack. When the engine requires more fuel, it can only get it if injection duration increases. The governor senses the need for fuel and moves the rack. The rack is a straight gear that meshes with gears on each plunger. Moving the rack causes the plungers to rotate. The plungers rotate slightly in their bores so that the scroll keeps the ports closed longer, increasing duration. This is called the fuel on position, as shown in number 1. As demand for fuel lessens, the rack moves toward the fuel off position, number 2, and the ports open sooner. Mechanical governors use a system of flyweights and springs to move the control rack. The springs always try to move the rack to fuel on. The flyweights always try to move the rack to fuel off. When the forces are balanced, the engine operates at a stable RPM. Fuel delivery directly affects engine speed and horsepower output. Increased fuel delivery increases engine output. Governors regulate fuel delivery to control engine speed between a low RPM setting and a high RPM setting, called low and high idle. Governors are usually mounted on the rear of the fuel injection pump. A timing advance unit advances or retards fuel injection by altering the fuel pump camshaft rotation. Fuel injection timing can be advanced or retarded. Advanced timing means fuel is injected sooner. Retard timing means fuel is injected later. The fuel system cannot operate in isolation from other engine systems. In particular, the air intake system is critical. Fuel will not burn completely unless there is enough air. The fuel ratio control ensures there is the right amount of fuel injected for the amount of air present in the cylinder. It senses boost pressure and will override the governor to prevent excess fuel from being injected. This helps control emissions and improves fuel efficiency. The fuel ratio control is mounted on the governor. On an electronic unit injection system, the rack, the mechanical governor, timing advance, and fuel ratio control are replaced by the electronic control module, ECM, and several solenoids or sensors. In place of a timing advance mechanism, a timing wheel and sensor monitor engine speed electronically. All of the functions performed by the mechanical units are handled electronically, giving better accuracy and reliability. The ECM senses engine speed and load and adjusts timing and duration automatically. The advantages of unit injection are higher injection pressures, even spray patterns, better atomization of fuel, better combustion, higher fuel efficiency, lower emissions, and greater reliability. Up to this point, you've learned about the various components of the fuel injection pump and how the timing advance unit and governor work to adjust the burn window. Now, let's look at how it all works together during engine operation.
During actual operation, the engine is usually working under load. The governor determines what engine RPM is correct for the applied load and moves the rack to fuel on or fuel off to establish the right RPM. The timing advance mechanism senses the increase or decrease in RPM and varies the injection timing to start the burn window at the correct location.
Low idle is the lowest speed at which the engine is allowed to run under no load. The fuel injection pumps are positioned so that minimum amounts of fuel are delivered to the engine. High idle is the maximum RPM the engine is allowed to run under no load. All diesel engines are given a rating called full load at rated speed. This is the RPM at which the engine delivers rated horsepower when fully loaded. The engine is operating under load, and the governor flyweights and springs are stabilized to provide a constant RPM. Sometimes engines are operated in such a way that the RPM is forced to exceed the high idle RPM. The governor shuts the fuel off, but the engine still exceeds the high idle speed. This is called overspeed or overrun and is usually the result of operator error. Sometimes engines are loaded too heavily, and even though the governor moves the rack to the full fuel-on position, the engine RPM does not increase. This is called lug operation. Under these circumstances, the governor is unable to match the horsepower requirements since no more fuel is available. In this segment, you'll learn about specific gravity, viscosity, cloud point, sulfur, and contaminants. You'll understand API rating and how it affects engine performance. And you'll understand cetane index and how a low rating affects engine ignition. Fuel produces power in a diesel engine when it is atomized and mixed with air in the combustion chamber. Pressure caused by the piston rising in the cylinder causes a rapid temperature increase. When fuel is injected, the fuel-air mixture ignites, and the energy of the fuel is released. A perfect fuel would burn completely, leaving no residue or smoke products. However, there is no perfect fuel. Fuel quality affects the performance and maintenance of any diesel engine. It's important to understand basic fuel properties to be able to judge fuel quality. These properties have an impact on the operation of a diesel engine and its fuel handling and fuel treatment systems. The specific gravity of the diesel fuel in Sample 1 is the weight of a fixed volume of fuel compared to the weight of the same volume of water found in Sample 2, while at the same temperature. The higher the specific gravity, the heavier the fuel. Heavier fuels have more energy or power per volume for the engine to use. Specific gravity can be measured on the American Petroleum Institute API scale. The scale is inverse to the specific gravity. The higher the API number, the lighter the fuel. Fuel with a low API number provides more horsepower. Caterpillar recommends 35 degrees API minimum fuel. Kerosene might have a measurement of between 40 and 44 degrees API. Viscosity is a measure of a liquid's resistance to flow. High viscosity means the fuel is thick and does not flow as easily. Fuel with the wrong viscosity, either too high or too low, can cause engine damage. Cloud point is that temperature at which a cloud or haze appears in the fuel. This appearance is caused by the temperature falling below the melting point of waxes or paraffins that occur naturally in petroleum products. The cloud point of the fuel must be below the lowest outside or ambient temperature to prevent filters from plugging. Cloud point is determined by the refiner. Sulfur is an element that occurs naturally in all crude oils. You should be aware of your fuel sulfur content. Sulfur over 0.5% can severely reduce engine life unless proper steps are taken. When diesel fuel containing sulfur is burned in an engine's combustion chamber, oxides from sulfur form and react with water vapor to create sulfuric acid. If these acid vapors condense, they chemically attack the metal surfaces of valve guides, cylinder liners, and may affect bearings. To limit sulfuric acid formation, keep engine temperatures above 175 degrees Fahrenheit or 80 degrees Celsius to limit condensation. Use oil with a TBN sufficient to counteract acid formation. The cetane index is a measure of the ignition quality of fuel which affects engine starting and acceleration. The higher the cetane rating, the more quickly the fuel will ignite. Cetane is rated using an index. Caterpillar recommends a 35 cetane for pre-combustion chamber fuel systems and a 40 cetane for direct injection fuel systems. Fuel with a low cetane number can cause ignition delay, starting difficulties, and engine knock. It can also cause poor fuel economy, a loss of power, and sometimes engine damage. And you might notice white smoke and odor at startup on colder days. Cetane improver additives can often reduce white smoke during engine startup in cold weather. Contaminants in the fuel can also affect engine performance. Contaminants are foreign elements which can get into fuel and cause problems. The two most common contaminants are water and sediment. Water can become a contaminant if it's introduced into the fuel during shipment or if condensation occurs. Excess water in fuel can cause fuel pump damage if fuel is used to lubricate the pump. Sediment consists of items like rust, scale, weld slag, dirt, and other debris that often get into fuel tanks and cause problems. All fuel should be cleaned by the primary and final fuel filters on the engine. After completing this topic, you'll understand common diesel engine starting systems and identify the components of each system. In this segment, you'll learn that cranking speed is more important than cranking duration for a diesel engine. You'll learn about electrical and air starting systems and understand the unique components used in each system. Starting systems operate by cranking the engine to build up enough compression and heat to ignite the fuel. On all starting systems, a cranking motor turns the ring gear and flywheel. As the flywheel turns, air is compressed inside the cylinders. Cranking speed is more critical to starting than cranking duration because speed determines the amount of heat generated in the cylinder. Cranking motors are powered by electricity or air. An electrical starting system has number 1, batteries, number 2, a cranking motor with a solenoid switch, 3, a starter switch, and 4, wires and cable. When the key start switch is on, the battery provides electrical power to the components in the starting system. The cranking motor converts electrical energy to mechanical energy. You might also find a master switch which disconnects the batteries, or a neutral switch which prevents the starting circuits from closing when the transmission is in gear. An air starting system consists of 1, an air tank, 2, a push-button valve, 3, a relay valve, 4, a cranking motor, and 5, a pinion. An air starting system uses compressed air to run the cranking motor. They have a faster cranking speed than an electric starting system. Air systems are common on off-highway trucks. The drawback with an air system is that you have only 1 or 2 attempts before exhausting the air supply. The air tank holds the compressed air. Control or relay valves open and close, allowing air to flow to the cranking motor. An on-off push-button valve starts the airflow to the relay valve diaphragm. The relay valve opens, sending air from the air tank to the cranking motor. The compressed air enters the cranking motor, turning it. Air is also directed onto a servo, which engages the pinion with the ring gear, turning it.